Thank you.
Thank you. Thank you very much. Thank you very much for coming. It's always a pleasure to be back here. And so I will talk about cosmic micro background. And of course, Princeton is a very special place for it. Has been always playing the leading role in any kinds of development in CMB. And I just wanted to show this animation that WMAP team created just to remind ourselves that galaxy exists. And this is really the nightmare for us, but let's see. So you go to the longer wavelength, and but by the time you go to the microwave, you are filled with this cosmic micro background. It's nice to see that indeed that's the brightest thing in the sky in the microwave. But when you improve the sensitivity of a detector, then you start seeing these ripples and galaxy, and then this is really the nice thing that we have that tells us about early universe. And here is the cosmic micro background. Light was emitted 13.8 billion years ago. They more or less come to us straight, and a bit of them will be scattered, but more or less come to us, and they tell us directly the information at the last scattering surface, but which is not quite the same as kind of beginning of the universe. We already wanted to know what happened before then. And to do that, we really need to use laws of physics. And then there was a quantum fluctuation, and they perturbed baryon photon plasma. There were sound waves, and we can see this here. But all of that is usually too complicated to explain the words, and therefore, I had a really wonderful experience lately. When we do the public outreach, what we do typically is to go to schools, or people come to the museum, we give lectures there, or we have organized some kind of public events where lots of people come, listen to whatever professors have to say. And that's usually very unsuccessful because we do research, but we're not really good at communicating them. So therefore, not everybody, but but usually, okay. So at the University of Tokyo a few years ago, we organized a very unique workshop. The workshop that was targeting only the science communicators. Then, so this science communicator defined in a very broad sense. So there were curators, there were people working on planetarium, but they also had movie directors, poets, musicians, artists. So everybody who loved the universe, they wanted to do something about it, but they necessarily didn't really know the cutting-edge research results. So I went to University of Tokyo to give a lecture on the cosmic micro background. Then one of the audience was movie director Hiromitsu Kosaka here, who was specialized in the full dome projection of the movie. So it's not the typical movie that you see on the flat screen, but it's projected on the full dome of the planetarium. And then he created this horizon beyond the edge of the visible universe. This is a full dome movie, which was created in both Japanese and English. Japanese version has been shown at the multiple museums in Japan. An English version has been shown at the multiple competitions, international competitions for full dome movies. We luckily won multiple awards. So hopefully this will be also shown at the multiple museums in the world. And today, I cannot really show you the full dome projection, but I just wanted to let you see the bit of it on the screen. But now you have to imagine that the center will be zenith, and then here will be in front of you, here will be the back of you. So you have to imagine that, right? I'm sure you can do it. There you go.
The cosmic background radiation is the wall at the edge of the visible universe. We cannot see directly the further past beyond this wall. But these temperature fluctuations may tell us what happened in the further past.
The conditions beyond the wall of the cosmic background radiation can be thought of as a liquid with high temperature and high density. You could say it was like a hot soup. Something happened behind this wall that made waves, which can be seen in the fluctuations in the cosmic background radiation. There must have been a grand sound that shook the universe. We can learn a great deal about the universe if we can extract this cosmic sound. The origin of the sound would be the moment of the birth of the universe.
Okay, yeah, so I guess remarkable, I know, sorry Jim, sorry Rashid, sorry. I know that, yeah. So, but now, despite some details, minor details, right, some troubles, it's a remarkably accurate description of what we are seeing. I mean, you had something at the beginning, then they created perturbations in plasma in the early universe. They create sound waves, and they just show up at the last scattering surface. But now we can do evolution backward in time and try to learn what the initial condition was. That's exactly what we do. And this movie really makes it easy to explain it to the public audience. So this movie director is not a scientist. He just came up with this. And first time I saw this, wow, this is very accurate. So, and they really know how to penetrate through people's mind. So, for example, this movie was seen by lots of people in Japan already. And this is the kind of impact you can have, much more than you might dream of, right? So I think this kind of having targeted workshop for science communicators may be really the one successful model where we can do public outreach. Okay, now, so as you have seen, you have this power spectrum of sound waves that we measure on the sky, and these sound waves also produce polarization. So we have this so-called E-mode polarization power spectrum, which are gravitational lensed, shown by Matthias, and you produce this thing that's been measured. So it's remarkable that all of these things have been measured. And now, just in case that you haven't seen the power spectrum, which is very unlikely, but anyway. So here, on this diagram, if you go to the left, you are looking at wavelengths of the fluctuation that's as big as the whole sky. And as you go to the right, higher multiples, you start seeing smaller structures. Then you've done all of that, and then you put them all together back, you recover the original temperature map. Yeah, so that's very nice. All right, good. So I think, of course, I'm not qualified to say things like this, but seeing the diagram like that really teaches us important lesson. So when Rashid and Jim came up with this sound waves in 1970, they thought that they would never be measured. Okay, we have the record because Jim wrote this story in the annual review on Astrophysics, and he thought that he predicted this, but at the time CMB was not even a black body, so he thought he wouldn't know what's going on, so he would just switch field to large-scale structure, which is super successful. Huh? And Rashid was told by Jakub Zeldovich that this, come on, you cannot put this in abstract. He will remove it, but physics is beautiful, so you should publish it. These kind of stories is remarkable, right? Of course, now young people wouldn't even dream that they were saying things like that. But then, of course, once experimentalists are convinced that this is a very important thing to do, from the detection of the power spectrum on larger scales, it took only 25 years to improve the sensitivity by 7 orders of magnitude in power. And this was enabled by amazing progress in the sensitivity of detectors. So now you have a handful of detectors here down to hundreds of thousands of detectors here. If we weren't for CMB, we wouldn't have this. There was really no reason to build microwave sensors, got 100,000 of them, and put them on the focal plane. There's absolutely no reason for that. But because of the CMB, and once experimenters are convinced that this is something that's worth spending 10 years or 20 years of their life, this happens, right? So I guess what I wanted to say is that if you go to the conference and young people are very ambitious and they tell you the effects are picokelvin or nanokelvin, that's fine, no? I mean, you should never say things like it's too small to see. Because history tells you that if the effect is interesting, and if you manage to convince experimentalists to look for it, this might happen. So I just wanted to say that. I think this is a beautiful lesson to be learned from here. Now, so what are you going to do? Next 10 to 15 years, we want to see this B-mode polarization from the gravitational waves. That will be the topic of today's colloquium. Okay, small, but you never know. We'll just keep looking for it. All right. So now, to that end, what we are going to do is to send yet another satellite. This time, will be specialized in polarization measurements. So we send this to L2 with a few thousand TS barometers in space. And on May 21st, we heard a wonderful news that the JAXA has chosen LightBird as the next mission. So we go to L2. And this is the JAXA-led mission, which is a remarkable thing because Japan has never built satellites on CMB before. And now we have participation from USA, Canada, and Europe. Japanese were sort of traumatized by this Nagoya Berkeley experiment before, and nobody wanted to work on this ever again. But now it's kind of forgotten. So we're recovering from trauma. Now we're ready to go. Yeah, very good. Okay. All right, so CMB told us something quite remarkable. We saw fluctuations in temperature, which implies that there was a fluctuation in the matter distribution. Then when there was a matter, it accretes matter and grows, and they finally produce first stars, galaxies, sun, planets, life, all of that. So that's really a remarkable story. But is that really true, right? So that's a standard scenario. But what generated the initial fluctuation? Because we saw the fluctuations at last scattering surface, but where they came from. So that would be the outstanding question. And the leading idea is that they came from quantum mechanical fluctuations. So in the early universe, time was very short. Because time was very short, you could borrow lots of energy from the vacuum, and they would create seed for galaxy formation. But of course, quantum mechanical fluctuations have very short wavelength. Galaxies are big. So how would you make the connection? And the usual story we tell is that there was a period of accelerated expansion, inflation, and they would stretch very small wavelengths of quantum mechanical fluctuation to large scales, and then they seed galaxy formation. Is that really true? Okay? And the inflation predicts that there were scalar perturbations, density fluctuations, that will be responsible for sound waves that you saw already, as well as these tensor perturbations, which will be gravitational waves. Okay, they distort this distance between 2 points in anisotropic way. They conserve areas or volume, therefore they would not produce density perturbations. They only produce tensor perturbations. So we have this distance between 2 points modified in this way. So this zeta will be the perturbation to the determinant of the metric. So therefore, that will be density perturbation. Hij is a traceless and transverse, so they do not produce a determinant. They do not alter determinant. So that's the tensor perturbation. And then we have this distortion, right? So how do we measure that? All right, well, so we all learned that when you have the two mirrors, you have the laser from the left, you beam split, and then you shift the phase of the laser so that when they come back and combined, crest and troughs of the lights will be canceled, you see no signal. That will be the initial configuration when you have gravitational waves coming in. The distance between 2 points will change in anisotropic way, and you see the signal. Okay, that's the great idea. And then it has been very successful. So they detected the gravitational waves from binary black holes in this way. But the wavelengths of the gravitational waves you can detect in this way will be essentially the size of the Earth. Or if you send the satellites to some orbits around Earth and have a bigger baseline, you can maybe detect gravitational waves with wavelengths of million kilometers, but never kind of billions of light years that you would expect to see for gravitational wave from inflation. So how do you even go about measuring it? Okay, so then you have CMB. So you have isotropic electromagnetic fields. So you essentially use the universe as a detector. Then gravitational waves are passing by. They stretch space. So when they stretch space, wavelengths get stretched as well. Where wavelengths is stretched, that's a lower energy photon. So you see, if you put the electron over here, electron will see colder photons from the horizontal axis, hotter photons coming from the vertical axis. And when this photon is scattered and coming toward you, then they are polarized. Why? Because, where, for example, we have the car and there's a windshield and there's a sunshine coming from the above, gets reflected, it's horizontally polarized. So essentially, you need to have anisotropic incident light and also scattering or reflection. How do we know that? Because when you then buy polarized sunglasses, which would transmit only the vertically polarized emission and blocks horizontal polarization, you see through the car. Okay? So that's very nice. Of course, the universe doesn't have a preferred direction. I think in late 1960s, Martin Rees wrote a paper that CMB would be polarized if the universe was anisotropic. That was the first paper on the polarization. But later, people realized that although the universe is isotropic on large scales, locally, you can produce anisotropy around an electron when you have gravitational waves passing by. Right? That's the key realization. OK, very good. So now we have the gravitational wave propagation equation in vacuum. And now you just quantize this, yeah, according to these people. Then they will give the variance or power spectrum of the gravitational waves, which is so-called scaling invariant. Namely, you have this Hubble expansion rate during inflation, which is more or less constant. It's decreasing over time slowly, but it's very much constant. Therefore, you get, this is almost K independent. K is a wave number. So you get something called scaling invariant spectrum of gravitational waves. Namely, it doesn't matter whether wavelengths of gravitational wave today will be 1 centimeter or 1 meter or 1 kilometer. Doesn't matter, right? They all have the same amplitude initially. But then they are processed by the expansion of the universe. So if you write down this equation in more kind of user-friendly manner, then you have the double dots, so time derivatives, and A will be the scale factor. So this will be the 3 times Hubble expansion rate. This is the wave number. So this is the spatial derivative. So essentially, gravitational waves are redshifted. So they're sensitive to how the universe expands. And so now you can kind of do the exercise. When you take the limit where wavelengths of the fluctuation is much, much greater than the Hubble length, which means this derivative term will be negligible compared to the expansion term. Then you don't have this term here, right? So then solution would be H constant will be a solution. And you have another solution that's a decaying mode. So on large scales, when you ignore this term, H will be conserved. That's a great news, because if you look at the long wavelength gravitational waves, they remember what happened at the beginning of the universe. If you take the opposite limit, you take this to be much larger, so this will be negligible, then you have a decaying solution. So on large scales, gravitational wave is conserved. Subhorizon scales, amplitude of gravitational wave decays. So we can use this to really see the initial condition of the universe. That's the amazing gift that we have. Now, but then let me explain this concept of gravitational wave entering the horizon. It's a bit tricky concept, but it's important. So inflation generated quantum mechanically the gravitational waves at all wavelengths. So as gravitational waves are produced on small scales, inflation stretches the wavelength to larger scales. Produced, stretched, and they all have more or less the same amplitude. That's the initial condition. Then as the universe expands, the horizon size grows, and then you can see more and more longer and longer wavelengths of the fluctuations. So that's what we call fluctuation entering the horizon. So namely, at the initial time, let's say you had fluctuation with various wavelengths. This is the physical length, so they are stretched over time. The wavelength is stretched over time. Today, it will be 10 gigaparsec. Today will be 1 megaparsec. This is the horizon size of the universe. Okay? So as time goes by, here, for example, 1 megaparsec fluctuation now is below horizon size. So they start to decay. Here, gravitational wave amplitude are all constant. They are conserved. But here, they decay, okay, as they evolve. So these gravitational waves that existed in inflation are reprocessed, the process by expansion of the universe. And because gravitational waves are relativistic particles, if you take the point of view of particles, their energy density goes down like energy density of the radiation. So as the universe expands, it decays like 1 over 8 to the 4th power. Okay? So during radiation era, however, background density also decays like 1 over 8 to the 4. So ratio of the energy density in gravitational wave to the total energy density of the universe is a constant. Okay? So therefore, if you take the ratio, this ratio, omega, doesn't change over time. Which means if you started out with this energy density spectrum of the gravitational wave, they all evolve. They can remain constant. Okay? So that's what you get. But actual spectrum hasn't been seen yet. So this is theoretical, but would have these structures here. That's very interesting. Okay? So one thing that's interesting to note is that during the radiation era, lots of exciting things are happening. At a few hundred MeV, quarks will be confined into hadrons. Now quarks are very light. Before they are confined into hadrons, they're all relativistic. But once quark-hadron transition occurs, they disappear out of radiation. Okay? So suddenly, background radiation energy density drops. Okay? Because this is the ratio of the gravitational wave energy density to the total energy density, denominator suddenly drops. So you get suddenly an enhancement. This is the quark-hadron phase transition. Here now, neutrinos start to decouple from the thermal plasma. Weak interactions are too weak to let neutrinos interact with rest of the leptons. Neutrinos freely propagate. Now, neutrinos act as a viscosity for gravitational waves. They actually damp slightly the amplitude of gravitational waves. So you get a slight decrease due to neutrino viscosity. Then, shortly after that, electron positrons annihilate. Now, at the energy scale of about 1 MeV or half MeV, you get positron electron annihilates, and they also disappear from the radiation. So you get a bit of enhancement here, right? This is very interesting. So in principle, gravitational wave spectrum, if you ever see it, seriously, no? Remember what I said at the beginning of the talk? This is like a time machine. You can see the entire thermal history of the universe. Now, what is this? Here, this is 1 TeV. If there was supersymmetry, okay, and then masses of supersymmetric particle we never see so far, maybe bigger than 1 TeV, or maybe 10, I don't know, like 1 TeV, let's say, then they become massive and disappear out of the radiation. Because you can see that too. Now here, this corresponds to the modes that enter the horizon during matter era. During the matter era, background density decays like 1 over the cubed. Therefore, the later the gravitational wave enter the horizon, less they decay compared to background density. That's why when you see the fluctuation entering the horizon today, that will have the biggest amplitude. Yeah. So this will be a wonderful thing to see. But unfortunately, so far, sensitivity of gravitational wave detectors are not quite there yet. So this pulsar timing array, sensitive to about nanohertz, laser interferometers like LIGO or LISA, they will be probing millihertz to decihertz to kilohertz. So they're here. They are nowhere near probing this. So so far, CMB is really the most realistic tool to see this kind of thing. And it's 10 to the minus 18 hertz. It's a convenient number to remember. But that's really billions of light years, if you think about it. It's remarkable. No astrophysical sources can ever create gravitational wave of that wavelength. That's why we're convinced that if we see gravitational wave of that wavelength in CMB, it got to be coming from our universe. Right? So that
we need to worry about the oscillatory signals in that power spectrum.
You don't have to. If you had a very instrumental sensitive design of instrument that's very, very narrow band, then you can see oscillation. But in most cases, we don't. So we have to just binned, right? We only see the binned version of it.
Maybe the question is the origin of the white stripes.
These are numerical, numerical artifacts. Yes, indeed. Yes.
So you show the PTA and interferometers at the top there, but is there vertical position in the graph representative, or are they off the scale, or how much an improvement?
Sure. Yeah. So I don't have that plot, but I think interferometer here will be somewhere. Let's see, determines 10, right? So it's yeah. In fact, I think somewhere here at the moment. PTA will be somewhere here also. So it's very far away. Yeah.
And are there foregrounds that would make it impossible?
So I think that's a very interesting question. You have the stochastic astrophysical background coming from unresolved mergers of neutron stars and black holes, right? So they will give you some interesting signatures. I mean, this stochastic background here. How to distinguish between them will be tricky. One possibility that I will talk about later is that this stochastic background could be circularly polarized. And in that case, if that's the case, okay, you can distinguish between astrophysical background in this. Then you might actually have to redesign LISA because current LISA can't measure circular polarization. But if you fly 2 LISAs and phase it properly, I mean, why not, no? How much more expensive does it get to fly 2 LISAs instead of 1? Okay, now, so cosmologists really want to measure this tensor to scalar ratio. This will be the squared amplitude of tensor divided by squared amplitude of the scalar. And so far, we haven't seen it yet. Therefore, this tensor to scalar ratio will be less than 0.06. And then this is the popular diagram. So on the vertical axis, this is the amplitude of gravitational waves. And on x-axis, we have this so-called primordial tilt that I didn't talk about. This will be the initial power spectrum shape of the scalar perturbation. And that hasn't been well measured. This is less than 1. That's a big deal. And then you have, however, now a bunch of, we haven't seen the gravitational waves. Therefore, we have this contours that do not close. This is 1 sigma. This is 2 sigma. We haven't seen it yet. Therefore, it doesn't close here. We want to see something like this. Now, these points come from some specific models of inflation. And the only thing that you take away from this is that some of the models are ruled out. Okay? So it's not the case that you can come up with arbitrary models anymore. They are subject to stringent observational tests. Yes?
Do you think that those models will just keep on getting lower as the constraints get lower, or do you think at some point?
Okay, so okay, now that you asked, let me tell you the story. So when I was a master's student, that's 1998, my advisor in Japan told me that this is the most natural model of inflation. Okay? And then I was shocked when we were working with as a WM team and ruled this out in 2006. I was like, wow. But then after that, I start to hear theorists saying, oh, come on, this is the most unnatural model. And then we started to talk about this other model here, right, which is gone. Right. So this is the current bound. No, this is gone. This is gone. I mean, people, yeah, indeed, people said this is the most natural. This is the most natural. Now people stop talking about this anymore. I mean, that's not true, actually. So now we have this R square inflation. This is one of the first inflation model prediction made in 1980. So this is still the best fit. But then people started to say, oh, actually, you know, this is attractor. No matter what you do in early universe physics, they all come here. It's remarkable that these papers appear. Indeed, indeed, if we don't see this model coming down, maybe people say, you know, actually this was never natural. It will come down. So you are right. But at this point, I say, okay, we'll just go out and measure them. Okay. Don't worry too much about theoretical predictions. They have been a very good guide, but now we are kind of getting there. No, we really want to see R that's about 100 times better than current limit. We just go out and measure them, yeah, and see what happens. Then to do that, we need to worry about galactic foreground. Okay, we have synchrotron, we have dust, we might have something else. Therefore, we take advantage of the space environment where we don't have to worry about atmospheric emission contamination. So we go from 40 gigahertz to 400 gigahertz, 15 frequency bands, and then just nail dust and synchrotron. Okay, and LightBird goes to L2 on JAXA H3 rocket. It's a pretty new rocket. And then we have three telescopes, low frequency telescope and high and mid frequency telescope, which is now here collectively called HFT, but high and mid frequency. So low frequency will be 34. That's the so central frequency is 40, but the bandwidth is there's a bandwidth. Therefore, the lowest possible frequency will be 34 to this. Okay. Reason why split this band into few telescopes is that when you try to measure microwaves, you need to make sure that your optics does not reflect back the CMB into the space again. So you need to have the anti-reflection coating. Now, but producing that over such a wide coverage in frequencies is not possible today. So you have to just cut the frequency coverage into 3 pieces and come up with a coating for each of the bandwidths. So that's why we need to have multiple telescopes. But that makes international collaboration easy because now Japan produces low frequency telescope, European produces high frequency telescope, and they can each claim we have a telescope. Yeah, so this is very nice. All right. Then, if everything works well, we measure power spectrum of gravitational waves in B-mode power spectrum. If the true value of R is 0.01, so this will be 6 times better than 6 times smaller than the current bound, then we have the definitive measurement of B-mode power spectrum over the wide range of multiples. So what I think is ideal for the community is that LightBird, I don't really want LightBird to be the first experiment to see B-mode. Could that be kind of sad? I mean, if you just see the one beam detection or maybe hint to sigma 3 sigma. Rather, if ground-based and balloon experiments see well before us, then we can have the definitive measurement of that. Yeah. So that would be very nice. And then, in terms of tensor to scalar ratio and the primordial tilt, this would be the contour if the central value of R was as predicted by first inflation model by Alexei Stravinsky in 1980. So this is the most popular model, right? And this yellow is so-called alpha attractor. So these people say this is attractor. And so that's a range of predictions they make. Gray is the current bound. And this will be the bound from LightBird if we did not see gravitational waves. Okay? So rather I want to be here or above here. Yeah. Okay, now, wait a minute. This sounds all nice, but are we sure that this is really what happened, in the early universe? Aren't we forgetting something? Aren't we forgetting the right-hand side of Einstein's equation? Okay, so we always talked about vacuum solution, but why, right? We don't really understand physics of inflation. We don't really understand particle contents of the inflation. If there are matter sources, they surely produce gravitational waves. Why not? The reason why people are kind of struggling to get that working was that there's a theorem saying that if the background of space-time is homogeneous and isotropic, scalar and vector perturbations cannot produce tensor perturbation at the linear order in perturbation. Now, they can do it at second order, okay? But when they produce second order when the second order perturbation in scalar and vector fields produces tensor perturbation, they also produce at the second order the scalar perturbation, which will be too big to be accommodated by Planck measurements of the beautiful power spectrum you've seen. So, for example, Matthias and collaborators try very hard to produce gravitational wave in this way by second order perturbation, but then they came up with the robust conclusion that you just can't do it because you screw up the scalar sector. But then in 2013, suddenly the situation changed. People realized that SU2 gauge fields can actually produce gravitational wave at the linear order. And so I will tell you a bit about that. But the one thing I want to say, therefore, is that you shouldn't really, this is kind of, I'm kind of telling myself 5 years ago something, because we always said things like, when we measure B-mode polarization from the gravitational wave, that's a proof that the gravity was quantized. It's a first evidence of the quantum gravity. I mean, we've seen this in the media right after Bicep collaboration announced the discovery, okay? But that's not true. I mean, even if their measurement was B-mode from gravitational wave, you shouldn't be able to say that so immediately, okay, until you really do the homework to prove that it was, well, at least to check the consistency with the vacuum solution. There's really no reason why you should ignore the right-hand side. And we have several examples that can actually give you such a thing. So now, so far, experimental strategy so far was that we detect CMB polarization in multiple frequencies so that we show it's a black body spectrum. It's CMB. Okay? Then we check for scale invariance. Is that scale invariant? No, is kind of consistent with the initial gravitational wave whose amplitude is constant over wide wavelength? If yes, you announce the discovery. If not, you scratch your head and then, I don't know, go to Triumph and have lots of beers.
So is it scale invariant? I mean, the temperature of power spectrum is not quite scale invariant.
That's right, yeah.
Is there a sense in which
it's exactly the same.
It's the same?
Yeah,
Do you
yeah.
expect the same end, or
So
not
yeah,
the same end, but
it's not the same, but it's similar. Yeah, that's right. Now, the new standard is that we have a bit more homework to do, okay? So up until here is fine, but when you have matter fields which violate parity, then produce gravitational waves. These gravitational waves are circularly polarized. If the parity is violated in the universe, you can have cross-correlation between temperature and B-mode polarization, or cross-correlation between E-mode polarization and B-mode polarization, which wouldn't exist otherwise. That you can use to detect parity violation in the gravitational waves. And also, you should really study whether perturbations are Gaussian, because the vacuum fluctuations, ground state of the free non-interacting fields have a Gaussian wave function. But if you produce this from matter sources, there's no reason why they are Gaussian. In fact, most of the times, they're completely non-Gaussian. So until you check these additional things, you cannot claim that you've discovered quantum nature of space-time. so easily. Okay? It's tempting, but you shouldn't do it. Yeah? So, but if not, okay, you may have just discovered new physics during inflation. I mean, come on, vacuum fluctuation, it's kind of boring, no? It's just vacuum fluctuation. You don't really learn too much about inflation if you just discover it, no? You learn something, but that's a full stop, okay? It'll be more exciting to see signature of the, more signature of the particle physics. But when I said things like that, and people say, oh, Eiichiro, come on, no, I don't want to listen to you anymore. Are you just complicating things too much? But it's not necessarily because, I mean, standard model has gauge fields, and these things have the right to exist in the early universe. There are plenty of them. Energy density of these additional fields is known to be small compared to the energy density of inflaton field from the Planck measurement, double mapping Planck measurements. We know that, okay? But gravitational wave energy density is really small. So even if you had the super subdominant energy density component in the universe, like gauge fields, they can produce lots of gravitational waves. Okay? And people working on string theory always told us that it's you can't create R that's bigger than 0.001. It's impossible. Okay? Most people say that. That statement is true only for the vacuum contribution. If you have gauge fields, which they do in string theory, they produce lots of gravitational waves, and they can easily, even string theory easily produces R that's bigger than 10 to the minus 3. And these gauge fields can be responsible for reheating of the universe. They may produce baryon number. They do lots of other things. So you have suddenly connection between various different observables. Like, let's say, it would be cool, kind of, right? We know baryons exist. We exist, right? So we have this baryon number, which is very small compared to the photon entropy. Nobody knows why. But if that number is connected to gravitational wave that we see in the CMB, wouldn't that be really exciting? Yeah? So we have lots of more phenomenologies, so we can learn more. Okay? Now, let me spend last 5 minutes just briefly flashing bit of the detail of the model, because otherwise I'll be just bullshitting, okay? Because I just need to show you some calculation that back up my statements, right? So, all right, good. Now, we have general relativity. We have inflaton. This is Lagrangian, which I don't want to talk about because I don't understand. Nobody understands what the inflation is. Just let them give us the background. Okay? Then I have lots of particles. So we have scalar fields, axions, which are coupled to gauge fields in this Chern-Simon term. Good. Okay. So this is very nice because we have now axion and SU2 gauge fields which are playing on this Dozita playground. Background is fixed. If they start to affect background, these things are very complicated. But once the background is fixed, we can calculate everything, what they do. Now, if you can't imagine what the SU2 field actually is, for this purpose of this talk, it's OK to say that you have 3 vector fields, which are configured in a funny way, and then they interact each other. So this one vector here, one vector there, one vector there, they all interact each other somehow, right? That's the kind of picture you have. And a remarkable discovery made by Azadeh Maleknejad when she was a graduate student in Iran. She's now a postdoc at MPA. She realized, because before her, people thought the gauge fields, which have directions, they would not be able to produce inflation, which isotropizes everything. But she realized that SU2 gauge fields, because they have 3 vectors, they quickly, quite generally, they quickly settle into this special configuration where you have vector fields pointing in z direction, vector field pointing in x direction, vector field pointing in y direction. And this can support isotropic expansion. So you can have mean, average gauge fields in a background level, and that people didn't realize before. And then, shortly after that, pioneering work people realize that when you perturb gauge fields around these background gauge fields, you can actually have tensor, vector, and scalar perturbation all together. And these tensor perturbations can then mix with gravitons to source linearly the gravitational waves. This was a game changer. Okay, people didn't know this before. This was in 2013. So now you don't have to rely on the non-linear perturbations anymore. You can rely on linear perturbations in gauge fields, and you produce copious amount of gravitational waves. And our contribution was to show that these gravitational waves are completely non-Gaussian.
Can you explain
Yes.
how the fields are sourced?
Ah, very nice. Thank you. Yes.
And in particular, is the gravitational field, is the electromagnetic field source?
Yes. Yeah, yeah. Thank you. Thank you. So the key is the coupling to scalar field, indeed. So if you didn't have this coupling,
The first step you do is not the electromagnetic field. That's,
no, it is like a magnetic field.
but it is not.
It is not. However, if you didn't have this term, these are massless gauge fields. They just decay. They wouldn't be sourced because there's no mass term here. This is the only kinetic term and non-coupling term. In this situation, gauge fields just decay like radiation. There's nothing to source them, as you say.
Good.
But as scalar fields rolling down the potential,
And the scalar field is
chi
chi.
here, yeah. So it's rolling down the potential.
It has gradient potential. Gradient.
It's actually the kinetic term, so chi dot square. And then gauge fields drains energy from the kinetic term. So the chi field is pumping energy into gauge fields.
So what's pumping chi?
So when you have the inflation, this chi field is displaced from the minimum of the potential.
Why?
Because of the quantum fluctuations, kind of, you cannot put chi in the minimum.
Okay.
Yeah.
Chi is quantum fluctuation.
Yeah, so you can have the effective mean fields that displace from the minimum. As the universe expands, this slowly moves to the minimum of the potential.
Did it have to start off away from the minimum?
Otherwise, it would be very you could, but that would be a very fine-tuned configuration.
I see.
Yeah, yeah.
So you have a degree of freedom, the distance from minimum.
Yes, yes, indeed. And this changes the spectrum of the gravitational wave we produce. Because unless chi moves, there's no gravitational wave. Therefore, gravitational wave amplitude is proportional to chi dot. And how big chi dot is, and what the evolution of chi dot, you can have variety of spectrum of the gravitational waves. All right, so just quickly, okay? So you have gravitational waves here. Let me define circular polarization modes, left and right. And in usual equation motion in the vacuum, will be this equals 0. But indeed, because of this funny coupling, you have non-zero. You don't have to know what they are. They're just non-zero. Okay? All right. So these gravitational waves are now sourced by spin 2 degrees of freedom of the SU2 gauge fields. This equation motion now have this term here. Yeah, so it's because one way or the other, you should only pay attention to the sign here. So this minus and plus sign corresponds to helicity. One helicity of gravitational, one helicity of spin 2 fields has a minus sign, another has a plus sign. When you have a minus sign, the effective frequency square becomes imaginary. So it produces an exponential growth of spin 2 particles. Suddenly, it's a particle production of spin 2 particles in one helicity mode. The other helicity mode doesn't change. So then suddenly, you have the situation where you've got, let's see, completely circularly polarized gravitational waves. Yeah? Okay, let me actually, yeah? And another thing that's interesting is that, so this is, again, energy density spectrum versus frequency. Usual standard law is that you have this 1 over f squared, and then constant, and bumps and wiggles here, but otherwise constant. It's a scalar invariant spectrum. But when you have gravitational waves sourced by gauge fields, remember that you have to have a chi that's rolling down. Because it's rolling down, it speeds up more as you go to, as you approach the potential minimum. which means the later time fluctuation have bigger amplitude for gravitational waves. In this diagram, the modes that enter the horizon later will be produced in earlier time, the later time in the inflation. So these correspond to the modes that were generated later in inflation. This will be the modes that produced earlier in inflation. And this model naturally predicts that higher frequency modes have a high amplitude. Then this suddenly opens up the very interesting synergy between CMB and interferometer scales. So that's very nice. And these are completely circularly polarized. So what's shown here, this dotted curve is the super LISA. You have 2 copies of LISA to configure the circularly polarized gravitational waves. Then you can have this sensitivity curve here. This orange will be the sensitivity to unpolarized, uncircularly polarized thing. So it would be cool to see this. And astrophysical background wouldn't be circularly polarized. Each of the neutron star binary will be circularly polarized, but the collection of them wouldn't be circularly polarized. So you can distinguish them in this way.
BBM is more realistic.
Yes. At this point, anything is, because of this exciting gravitational wave discovery, now everybody wants to put money on it, right? So this is more realistic than before. I'm running out of time, so let me skip. I think I said pretty much everything I wanted to say. Summary. So using CMB polarization to find gravitational waves will be the next frontier. But not just the detection, detailed characterizations of that would tell us whether gravitational wave came from the vacuum or sources. Is it a scale invariant? Is it Gaussian? Is it a parity vibrating? That's very exciting. And now with LightBird, we hope that we can do this job. So I'll stop here. Thank you very much.